Thank you very much. I'm going to talk about dynamics of randomized row action methods for high-dimensional estimation. I'd like to start this talk by thinking about a very simple problem, just a linear inversion. Suppose you want to reconstruct a vector x, and you observe it through a linear system, so the output y can be written as a matrix A multiplied with x, potentially with noise. Now, if you want to reconstruct x, you can use least square, and the problem boils down to solving a minimization problem where each term is a quadratic term. It's a summation of quadratic functions. Now, a more general version of this problem is that you want to minimize the functions that can be written as a summation of a very large number of individual cost functions. And this is a fairly general framework. A lot of problems in machine learning signal processing, such as sparse recovery, image reconstruction, dictionary learning, sparse filtering can be formulated as special cases of this problem with choices of these cost functions, right? Okay. So of course there are a lot of applications, so I just highlight a few here. And going back to our problem, the linear version, the least square problem, has been studied for hundreds of years, and also the nonlinear version, the more general version, has also been studied. For example, in the statistics literature, it is sometimes known as the M estimator, and it's also studied in terms of regression and so on. But if you look at the recent literature, there are a lot of renewed interests in revisiting these problems, even for this linear least square problem. Okay? To me, these interests are spurred by the challenges associated with modern data sets. So we can consider data sets that are with very large dimensions n, and the number of equations m can also be very large. So in fact, they can be so large that the data have to be stored in a distributed fashion, or you can have access to very large-scale parallel computing environment, but with hundreds of thousands of cores, but each core can only handle a very small amount of memory. In both cases, we can only have access to partial portions of data sets at any given time, or the data can come in a streaming fashion, revealing these cost functions one at a time, okay? And there are also these challenges of directly dealing with non-convex problem instead of doing any convex relaxation. In this talk, I'm going to focus on a class of iterative methods that, to me, are well-equipped to handle some of these challenges. These are iterative methods with very efficient computational complexity, with low computational complexity per iteration, typically linear, and they can do partial updates, or they can do reconstruction on the fly when the data are still coming in without the need to wait for the entire data sets to be available. And also, a key component of this set of methods is randomness, and the randomness can come from different sources. They can come from the nature of the problem, because we are studying an ensemble of these optimization problems with drawn from a random ensemble, or they can be by design, and you want to introduce artificial randomness into the algorithm just to achieve performance guarantees, or they can be coming from the nature of the computational communication environment. You can do it on noisy circuits over noisy communication networks, okay? Now, what we want to do once we have an algorithm, we want to analyze it. The typical question is convergence, and because we are studying the regime where m and n are very large, people typically study phase transition behaviors. But in this talk, I'm going to focus on something further. We want to study the dynamics of these algorithms, meaning that we want to know the performance of these algorithms when they are still tending towards convergence at any given iteration, okay? All right, so here is a brief outline of this talk. I'm going to start with a simple case, a linear least square problem. Although the setting is very, very simple, I will show that there are still interesting problems, and there are even very hard open problems left for this in this setting. And then I'll move on to a more general nonlinear and in particular non-convex system of equations. I will show there is a very simple iterative randomized row action method with performance guarantees, okay? All right, so first, the linear version. So we want to consider the simplest possible case. That is a linear system of equations with no noise. So it's a consistent case. If you look at each equation, each equation gives you a linear constraint, and which is the affine subspace. And we know that the true signal or vector must live at the intersection of all these linear constraints. So a very simple algorithm is that you can start with any initial point, and you pick one constraint, a single constraint, and you project. And then pick the second constraint and project, and after a while, you're going to converge to true solution. This is a very simple idea and also a very old algorithm. This was first proposed by Kaczmarz. And depending on the community you're from, sometimes it is also known as the algebraic reconstruction technique, a special case of a projection onto a convex set. This algorithm is very simple. You go through your list of constraints. At any given time, you pick a constraint, you project or enforce that constraint, and you move on, right? Until you reach the very end and you start all over again. Okay? This is very simple, but it is a workhorse behind the invention of the first CT scanner, an invention that won Hounsfield and Cormack their 1979 Nobel Prize. And if you or your luggage go through an airport scanner, chances are that some variations of this method is still working behind the scene, right? So this method is also very easy to understand. It's relatively easy to convince yourself that after a while, you will converge to the true solution, but the true challenge is to quantify the speed of convergence, because the speed of convergence depends on the order at which you choose these constraints. Okay? This is one particular order, but if you use a different order, then you're going to have a faster convergence. Okay? But you don't know a priori what will be the optimal order, and you don't have a lot of computational resources to determine beforehand, because otherwise you would have to actually solve the least square problem. So practitioners know how to solve this problem. You can do randomization, right? You don't need to fix the order of these constraints. You can, at any given iteration, you can pick one constraint according to some probability distribution. But it was only fairly recently that Thomas Stromer and Roman Verschuning, they analyzed the performance of this randomized Kaczmarz algorithm. They consider a setting where you choose any particular row or constraint with a probability pi proportional to square norm of that row. Okay? That's a particular choice. It's not essential. And this shows that in this case, the MSE of this algorithm with the expectation taken over the random choices. So there's nothing random about the problem itself. The randomness comes from the choices the algorithm has made. And MSE converges to 0 exponentially fast, with exponent depends on the condition number. Okay? It's a nice upper bound of the MSE, and after that initial work, there's a large number of follow-up work, extending this work to noisy cases, to least square projection, and to also iterative random sketching. Instead of just, say, picking a row, you can have a Gaussian projection, a sketched version, and then do this type of efficient processing. Okay? But the game is that you want to analyze a version of this algorithm, and you want to show that the MSE has some sort of exponential convergence either to 0 or to an error floor, right? Okay. So and then what we recently we analyzed this algorithm. We found that there is a very simple and generic way of computing the exact MSE instead of a bound, an upper bound of the MSE. So here, this is the first thing I want to talk about here, and so here's a way to analyze this algorithm. So we have a recursive formula, for example, for this simple Kaczmarz algorithm. And because we care about the error, let's subtract from both sides of the equation the true signal, the true vector x. And we call the difference zk. Okay? Zk is the difference vector or error vector from the previous iteration to the new iteration. And the update is nothing but a matrix multiplication because it's a linear algorithm, right? And Q of k is a projection operator onto one of these constraints, right? Now, if you do recursion, then after k steps, what you obtain is a product of these projection operators multiplied with your initial error vector, okay? And because these are projection operators, they are non-expensive, okay? They are sort of contraction, so that's why this algorithm converges. But the only challenge is that these operators or these matrices are not strict contractions because the largest eigenvalue is equal to 1. But the nice thing is this is a randomized algorithm because at any given time you randomly pick one of these. So they satisfy this property of average contraction. Okay, so on average, this is a contraction operator, and then that's why you have exponential convergence. Now, here is the result that we obtained. We show that at any given iteration, n is the number of iterations you have, the MSE of the algorithm can be computed as a product of 3 terms. So the rightmost term depends on the initial condition, the initial error. And what drives this MSE down to 0 is the matrix here, and it is raised to the power of n, the number of iterations. And this matrix has this form. For now, we don't need to worry about the exact form of this matrix. We just need to know that this matrix is a strict contraction. The largest eigenvalue is strictly less than 1. Okay? Before I show how the idea behind this proof, let me just look at some numerical simulations. So on the figure to the left, we have simulation results over 2,000 iterations. Because this is a randomized algorithm, these gray lines are different realizations of this algorithm. And we have green and blue lines are the empirical MSE versus what the formula predicts. It's a verification of the formula that the formula is correct. We also show here the best bounds in the literature. Now, because the vertical axis is plotted in log scale, there is a fairly big gap between what the bounds is saying and what the actual MSE is saying. Now, the figure on the right is the same experiment, but with a different matrix. The matrix here is a real CT matrix using image reconstruction. For this real matrix, instead of a Gaussian matrix, the gap is even wider, right? Okay. So for practitioners, it's important from these two figures to see that to use the exact, more precise formula, because suppose your tolerance is 0.1, 10 to negative 1. If you only know about the bound, then you would have to run this algorithm 1,000 iterations. But if you know the MSE, you can stop after 100 iterations, right? Okay. So what is the idea behind the proof? This is the initial proof that we wrote down in the first paper showing this result using some matrix identities. But later we realized that there's a much better way, actually much simpler way of explaining why we can get an exact MSE. It's a very simple idea. The idea is the following. Because here we write out a recursion of this algorithm, this error vector from previous step multiplied with a random matrix QK, and is equal to the new error vector. Now, if you only want to compute the expectation of this error vector, because the choice that I make at any given iteration is independent of the current vector, and because this is a matrix vector multiplication, it's a linear, so they factorize. So we can take expectation of the matrix times expectation of the vector, and after iteration, you have expectation of the matrix raised to the power of k. Okay, that's a very simple scheme, but we don't want to compute expectation of the error vector. We want to compute expectation of a nonlinear term, which is the square norm of the error vector. But we can just do linearization by lifting, right? So because we know the MSE, which is a norm, square norm of a column vector, can be written as a trace of this column vector times its transpose, okay? So instead of tracking these vectors, we can just track the evolution of these rank 1 matrices. And these matrices are undergoing the similar linear, random linear recursion. So here you can write out this recursion. You have two matrices on both sides, but as far as the matrix elements are concerned, this is a linear operation, random linear operation. So you can just use a canonical product to get this in a very more explicit form. Then you can apply exactly the same idea as we show for the linear case to get the formula. So it's a very, very simple idea, right? But it also applies to a very large class of algorithms proposed in the literature, not only for this Kaczmarz, as long as it stays within the framework of random linear recursion, you can use this formula, okay? Now, once you have the formula, we know that the MSE go to 0 exponentially fast, and the speed of convergence really depends on the leading eigenvalue of that matrix, the kernel, right, okay? So this is the leading eigenvalue of that matrix is going to give us the error exponent, okay? And this matrix can be written as a linear combination of these canonical matrices with the combination weights pi to be the probability with which you sample the ith constraint. So there is this game of optimizing the sampling probability. You don't need to consider uniform, or you don't need to consider the scheme Stromer and Verschuning considered in their paper. You can say what is the best choice with the best distribution over which you want to sample so that the error exponent is maximized, okay? And this turns out to be a convex problem. You can solve it. Now here is just a numerical simulation for the case when the matrix has 3 columns. So each row is a point on this sphere. We can represent every dot. We use every dot to represent a row, and the color, the intensity of the color represents the probability. Okay, the lighter the color is, the lower the probability, and vice versa. Now, for this case, and we can see that this optimized result is sort of making sense because there are regions on the spheres that are very densely populated. That means that you have a lot of row vectors essentially pointing towards similar directions. And then for example, this is the region. And then the optimal sampling probability as obtained by solving this problem is low. Okay? And there are also regions where you have more sparsely populated regions, and then you assign higher probability. Okay? This is just an intuitive verification of if this optimal sampling probability makes sense. Now, the test, what practitioners really care about is if this optimization is useful. Now, here we do some comparison. After running 20 iterations, the blue curve is the performance of optimized sampling probability, and the green curve is uniform sampling. And we can see there is about 30 dB of improvement, and the red curve is a result of another optimized scheme sampling probability. The only difference is that we're optimizing over the true MSE, but that previous work is optimizing over the bound. Okay, and there is again a difference of about 10 dBs if we use the true MSE. Okay, so this is about optimizing sampling probability. Now, here is a very interesting numerical phenomenon that we observed through simulations, and it turned out to lead to a challenging open problem. Now, because this is a randomized algorithm, so every time we run this algorithm, we'll get different results. And this is a histogram. Suppose we run this algorithm over 1,000 independent trials, and we stop each trial at 500 iterations, and we plot the resulting MSE versus as a frequency. Okay, so the horizontal axis is the MSE, and the vertical axis is the percentage of times that we reach that particular MSE. And the green line is what the original bound is predicting. Clearly, it is fairly loose. And the red curve and the blue red line and blue lines are the empirical versus theoretical MSE. It's a match, it's a verification. But clearly, there's more to the story because you can see that the MSE is not a very typical representation of the performance, because the typical representation should be at the bulk, the center of this histogram. Because here, the horizontal axis in log scale, there is a 2 orders of magnitude difference between what MSE predicts and what, for example, the median of these realizations are actually achieving. So here is a different curve, but I don't think it's easy to see with this projector. So these are different realizations, and the MSE formula, the blue and the blue lines are a little bit pessimistic. Okay, and the reason is that if you want to compute the MSE, you are averaging over all these realizations, right? Now, on the far right, you have very, very low likelihood events, but their contributions are orders of magnitude higher than a typical representation. So by taking the expectation, you are being unduly influenced by these rare events, which in many cases you don't want to care about. Now, what we propose is to say that we don't want to study the original formulation, taking expectation of the MSE and then compute its rate. What we want to do is to first take the log so that the quantity is normalized of order 1, and then take expectation. That's going to be a more typical representation of the actual decay rate of this scheme. Okay? But the challenge is that studying the second component, which we call quenched error exponent, is very, very difficult because it is related to computing the Top-Lyapunov exponent of a product of random matrices. Okay? It is known to be fairly difficult, and it also had connection to the computing the free energy density of a one-dimensional disordered system. So, and what we use is some approximation that's inspired by methods in statistical physics, so-called replica method. Because we're dealing with exploitation of a log of random variable, this log of a number can be written as the derivative of z to the power of n, where n is equal to 0. And what we can compute is z to the n for n to be equal to even integers. Okay? So a very simple scheme is that let's compute z to the n for n equal to 2 and 4 and do an interpolation. Hopefully this curve is smooth enough, we can do interpolation, we can get this result. Another justification, this is a naive version of a replica method. Another way to explain this is to say that if we assume that this distribution is log normal, then this is going to be exact, because if you have log normal distribution, knowing the second and the fourth moment, which can be computed, uniquely determines the quantity that we want to compute. Okay? All right, so we obtained an approximate formula in terms of the quenched error exponent, and it's not a proof, this is only an approximation. But we did the experiment, we can see that indeed the quenched error exponent is a correction. It matches with the typical performance of these algorithms better than what the annealed or the MSE formula predicts. Okay, so, but there's still an open question in terms of how you would be able to compute the true quenched error exponent as we defined in this way. All right, okay. All right, I want to move on to the second part, which is about nonlinear problems and more general system, including non-convex systems. So the problem setting is the following. I think Eric, in his morning talk, you mentioned very similar settings. It's a regression problem. You want to estimate a vector x star, and you can measure it in terms of some sensing vectors. Because I come from signal processing community, I call these the sensing vectors. You take inner product between x and these sensing vectors, A of m, and you observe these inner products through a channel. Okay, it's a memoryless channel, meaning that there is a conditional probability of observing y given this inner product, and these measurements are conditionally independent. Okay, and there are a lot of cases in signal processing that this formulation arises in image reconstruction and so on. But for now, I'm going to focus on the problem of phase retrieval because it's a fairly challenging setting. The phase retrieval problem is that the y's is equal to the absolute value or equivalently is equal to squared version of the inner product. Okay, and you can add additional noise, for example, with a conditional probability density function. All right. So in the real value case, essentially what we're missing are the plus or minus 1 sign information. In the complex value case, we are missing the phase information. And that's the reason why this problem is called phase retrieval, because reconstructing x is equivalent to recovering the missing phase, right? Okay? And there are applications in X-ray crystallography, but there are also applications in communication, signal processing, where you care about this type of problems. Now, this is also a non-convex problem because of having this absolute value or squared, and the state-of-art solution is to consider convex relaxation. Okay, so you want to linearize your quadratic measurement by lifting. Again, it's a lifting idea. So instead of reconstructing x, you want to reconstruct a Rankle matrix, which is x times its transpose. In that setting, the quadratic measurement becomes a linear measurement in terms of these matrices. And what is non-convex is that you have to enforce the rank 1 constraint, and then you can relax that by minimize the nuclear norm. Okay, and these kind of problems can be solved by semi-definite programming. You can show very nice results. The only problem comes when you want to actually implement this algorithm, because the computational complexity of semi-definite programming can be very high. Okay, and presumably you are going to apply this algorithm on images where you have millions of pixels. Okay, there's no way that you can run an SDP for n in the range of millions. Okay, without doing a lot of optimization. Okay, all right. So this prompts us to consider a direct non-convex procedure for solving this convex problem. Instead of working with matrices, we want to work with vectors. Now, I want to just digress a little bit. What is the non-convex procedures that we consider? Remember, this is the linear version. Suppose we have the phase information, we can do iterative projection. But if you have missing phase, then the challenge is that suppose you have the true solution here, but because you don't have the sign information, for every possible subspace, there is a potential, alternative explanation for that, right? Because you can have plus or minus 1. And in the end, for each subspace, you have it's a mirror symmetric copy, and then you don't know which constraint you want to enforce, right? That's the challenge. Now, a very, very simple algorithm, this is the starting point of how we obtain this algorithm, but there are also explanation of this algorithm in terms of Newton's method, is that because we are missing the sign information, we can say that let's just use the sign information obtained by the current estimate as a surrogate. Okay, it's a very reasonable choice, and you can also obtain this algorithm by saying let's just do an incremental Newton's method. You will get exactly the same formulation. Now, and then here's the settings that we consider in analyzing this algorithm. We consider setting when first, the sensing vectors are random. They are IID Gaussian, okay? And we consider the case when n, the signal dimension, and the number equations are both very large, but with a constant ratio between them. We call alpha, okay? Typically, you want alpha to be greater than 1 because you're missing a lot of information you want to have in this oversampled region. And we want to consider this map estimator solving this map problem by doing incremental gradient descent. Okay, so at any given time, we pick one function, and then we just do a gradient descent step. And it's a one-pass algorithm. You never go back. Okay, so it's online. So once you have used one function, just say you don't use it anymore. Okay, it's a one-pass algorithm. All right, so under these settings, we can analyze our algorithm. So here is a special case for phase retrieval. This is a recursion. We don't need to worry about the details of recursion, but we just need to know that this is a Markov process in Rn because the states are the vectors, okay? But for an engineer, what we really care about is that location or the state of the algorithm. What we care about is the distance between the current estimate and the true signal, and the square distance. If you expand the distance, you can see that the distance can be written as a summation of 3 terms. The first term is the square norm of the true signal, which is fixed. Okay? The second term is the square norm of the current estimate. And third term is inner product between your current estimate and the true signal. Or geometrically, you don't really care about where your point is. You care about the angle made between your current vector and the true signal and the length of the current vector. So we call these two quantities bk and ck, where bk is a square norm and ck is the inner product. Okay? These are the quantities that we actually care about. And we can try to write out the dynamics linking the evolution of bk and ck. Okay? And there's no reason that we can expect to have a closed dynamics because these are only functions of a full Markov process. Okay? bk and ck, they should form a hidden Markov process. But in the case of IID Gaussian sensing vectors, or more generally in the case of IID random measurements, we can show that in the large n limit, bk and ck, the dynamics of themselves form a closed Markov chain. Okay? In other words, this is a dimensional reduction. Irrespective of size of n, we only need to work with a 2-dimensional Markov process, which is nicer. Okay, we can write out the exact form. This is only just an explanation for rotational symmetry. I don't have time to go through this. And then the key idea is that bk and ck, they form a closed 2-dimensional Markov process in R2. And here is the evolution from bk to bk plus 1, and some simulations. For every iteration of this algorithm, we can summarize the performance in terms of pointing R2, and this goes through a Markov process. Okay, and here U and V are jointly Gaussian, whose covariance matrix depends on the current value of bk and ck. So it's really a Markov process. Okay, but still, it's not very convenient to study a Markov process defined on R2, okay, because the state space is uncountable. But what is nice is that the step size here is 1 over n. That means when n is very large, this Markov process is making tiny updates. Okay, in the large n limit, this Markov process, the trajectories of this Markov process will converge to solutions of deterministic ordinary differential equations. Okay, this is sometimes known as the fluid limit of this Markov process, and we consider this fluid limit. We can derive the underlying ODEs. Okay, these two ODEs are coupled, and they are also nonlinear, right? And that shows that they can be used to predict the performance of this algorithm. And here are some simulations. On the left, we have the evolution of BT and CT, okay, angle and the norm. And the dots are Monte Carlo simulation results, average results. And the black lines are the solutions of deterministic ODEs. Okay, it's a very, very good match. And probably you cannot see from where you are, there are actually error bars. But because the concentration is so tight, it's difficult to see the error bar because the size of error bars are smaller than the size of these dots for n equal to 2,000. Okay, so we don't need to have very large n for this type of asymptotic predictions to be effective. And once we know these two quantities, we can compute MSE. The MSE has this fairly interesting behavior that it's not monotonically decreasing. Okay, there is an initial phase of increasing MSE followed by decreasing MSE. And this also shows the power of using this ODE method, because otherwise it will be pretty difficult to capture this behavior, right? Okay, all right. So there is one detail that I skipped, but it is a critically important detail. This is one of the conditions in achieving this ODE convergence is initialization. We have to initialize this algorithm correctly. And this initialization says that C, which is the inner product between your true signal and your initial vector, must be not equal to 0. Or geometrically, we're saying that you cannot start with initial point that is orthogonal to the true vector. Okay, that's the condition. And then this also can be explained. This two-dimensional Markov process can be understood as sort of a stochastic gradient descent on a two-dimensional potential field. And then there are trivial fixed points correspond to the case when you initialize your algorithm with an orthogonal vector. And we want to avoid these trivial fixed points, right? Now, in the low-dimensional case, it feels very simple to achieve this condition. As long as you're not orthogonal to the true signal, then this algorithm, this convergence will hold. But the challenge is that in the large n limit, if you randomly draw initial point, for example, from a IID Gaussian distribution, then the chances are that the initial point is orthogonal or uncorrelated with your true signal. That's a concentration measure on the equator on the high-dimensional sphere, right? Okay, so it's actually pretty challenging problem. And then we use a very simple but very nice algorithm first proposed in the paper of Netropoli and co-authors. They use a spectral method for initialization. The spectral method works as follows. What you construct is a matrix A is a linear combination of your measurement times the corresponding vector, measurement vector A and its transpose. So it's a linear combination of weighted rank-order matrices. Okay? And you find this matrix A and you compute its leading eigenvector. The claim is that the leading eigenvector is going to be correlated with the true signal. Okay? And there is a simple hand-wavy explanation. because A is a weighted average, is just an empirical average of a very large number of independent matrices. Because M is very large, then A should be close to the expectation of each random matrix. If you compute the expectation, you can see that the leading eigenvector of the expected matrix is exactly equal to the true signal. Okay? In other words, if your random matrix is close to the expected value, then the corresponding random eigenvector should be also close to the true value, and then you have this result. Okay? That's the explanation. And if you do numerical simulations, this is also working fairly well. So we did this simulation for n equal to 10,000, and we see this behavior. So the horizontal axis is the sampling ratio, m over n. Okay, the larger the ratio, the more oversampled you are. And the vertical axis is the correlation, squared inner product. Okay, the higher, the closer to 1, the better. And what we show here are the Monte Carlo simulation results, and with error bars. And clearly, you can see some interesting phenomenon here. So first of all, this kind of algorithm, they concentrate. Okay, for a reasonably large n, different realizations are fairly close to the expectation, and they also seem to be two different phases, right? Okay, so when alpha is less than this value, it seems that this algorithm is not effective. Okay, you have zero correlation. It's still orthogonal. But once alpha is greater than this value, then you start to see, suddenly you start to see correlations. And if you let alpha go to infinity, then this correlation will converge to 1. And this is the question that we want to understand. And this is a fairly recent result. I don't think I have time to go through the details. What we showed is that there is, first of all, a deterministic characterization in terms of the eigenvalue and also the inner product. It boils down to studying this function, L of mu, which is the largest eigenvalue of a linear combination of two matrices, P and Q. Okay, P is a part of A, and Q is also another part of A. And then we show that if you can compute this function, okay, that's not a given, but if you can compute this function, then you can solve a fixed point equation. L of mu is equal to A plus 1 over mu. There's a unique fixed point, mu star. And the value of this function at this fixed point is exactly equal to the largest eigenvalue. And the inner product can also be computed at this fixed point, if you know the function and its derivative, all right? This is a result that holds for any matrix. It does not need to be random. It works for any matrix, any size. It's a deterministic result, okay? But then to say more, because we want to compute this function, then we consider the case when the sensing vectors are already Gaussian, and in the large n case. In that case, it turns out it is possible to compute exactly what this function is. There is an implicit formula for computing this function, and for this function, it has sort of a phase transition behavior, which is related to this the BBP phase transition of the leading eigenvalue can, under certain condition, jump out of the bulk spectrum. All right. Okay. So here is some simulations, and the red curve is what we get analytically, and we can show that this is a verification of this result. All right. So just to summarize, we considered some randomized row action methods, and for the linear case, least square case, to study the MSE, we just showed a very simple but fairly general strategy. By doing lifting, you can linearize the dynamics, and then you can compute the MSE, or more generally, arbitrary even moments fairly simply. And then there is this very challenging question of understanding the quenched or typical performance of the algorithm versus the average performance of the algorithm. Now, for the nonlinear case, we study this online algorithm, and there is a dimension reduction argument, which allows us to study only a two-dimensional Markov process instead of an n-dimensional Markov process. And also in the large system limit, the two-dimensional Markov process can be completely described by deterministic ODEs, which are fairly useful analytical tools for analyzing these dynamics. All right, thanks for your attention.